Hi, I will finish section 14.2, exponential functions. I'm going to finish this section with an application to compound interest. So this is one of the most useful applications of exponential functions. And it's compound interest. Okay, so I'm not going to go over the derivation of the formula. I'm just going to show you what the formula is on page 426. Okay, so if P dollars are deposited into an account paying an annual interest rate R, compounded n times a year, then after 3 years, the account will contain $8. According to the following formula, the amount in the account will be the initial deposit or principal times 1 plus R over N raised to the T over N. Okay, so all these variables mean the following. P is the principal. Is the principal or initial deposit or initial amount. A is the amount in the account after 3 years. Next, R is the interest rate. This is usually given as a percent. So when you do the arithmetic, you must convert it to decimal. And N is the compounding frequency or compounding periods per year. Like if interest is compounded once a year, N is equal to 1. If it is compounded semi-annually, N is equal to 2. If it's compounded quarterly, there are 4 quarters, so that's going to be 4. If it's compounded monthly, there are 12 months, so N is equal to 12, and so on. Okay, so let's suppose this example is not in the book. I'm going to type it, and this was on page 426. Okay, so here's an example that is not in the book. Let's suppose that $2,000 are deposited into an account paying 6% interest per year compounded monthly. Okay. This has 2 questions. Let's first find the amount in the account after 5 years with no withdrawals. And part B, we're going to find how much interest is earned after the 5-year period. So we're going to use the compound interest formula. Remember, the compound interest formula is A equal P times 1 plus R over N to the N times T. So we know from the context, we can see that the principal is 2,000. The interest rate is 6%. So when we do the arithmetic, we need to convert that interest rate, we need to convert it to decimal. And it is compounded monthly. So n is equal to 12. There are 12 months in a year, so it's compounded monthly. And we want to find the amount in the account after t years. So t is equal to 5. So the amount in the account after t years is going to be 2,000 times 1 plus 0.06 divided by 12 to the 12 times 5. So 0.06 over 12 is 0.005. So that's 2,000 times 1.005. And 12 times 5 is 60. So in this problems involving money, we're going to round the answer to the nearest cent. And this is what? This is 2,000 times 1.005 to the 60th power. So that's going to be $2,697 with 70 cents. Yeah, you share the calculator again. Okay, so that's approximately to a nearest cent. This is $2,697 with 70 cents. So that is the amount in the account after 5 years with no withdrawals. B, how much interest is earned after the 5-year period. So the interest is the amount in the account minus the principal. So this account generated almost $700 of interest. So this is $2,697 with 70 cents minus the initial deposit of 2,000. So the interest earned was $697 with 70 cents. So this is the interest earned. Okay, I'm going to copy the next example from the book. We're using the compound interest formula. Okay, so in the last example, we knew the principal and we knew we found the final amount. Now let's suppose that we know the final amount, how much you want to have in the account, and you want to know how much you should deposit to reach that amount. So find the present value or how much must be deposited. That will grow to 25,000 if interest is 3.2%, compounded quarterly for 11 quarters. So we don't know P. We know the amount. We know that the amount will be $25,000. We know the interest rate, 3.2% or 0.032. We know that it's compounded quarterly. And for 11 quarters, so that's going to be T. There are 4 quarters in a year, so that's going to be 11.4, or if you want, that's the same as 2.75. So 2 years and 3 quarters of a year. We are going to find P. Okay, so P times the principal times 1 plus The interest, this is time. This is not equal, this is times. The interest rate divided by the compounded frequency raised to the 4 times 11 over 4 is equal to 25,000. So 0.032 over 4 is 0.008. So that's plus 1 is 1.008. And then 4 times 11 over 4 is 11. That is equal to 25,000. And the principal is going to be 25,000 divided by 1.008 raised to the 11th power. So that is 25,000 divided by 1.008 to the 11th power. And that is going to be $22,902 with 4 cents. To the nearest integer or to the nearest cent is going to be 4 cents. Okay. So that's the amount that will grow to 25,000 during that period of time, during 2 3/4 of a year. And so we did one example where we wanted to find the final amount. And in the example we just did, we wanted to find the principal or the initial deposit. And in the next one, we want to find the interest rate. So find the required annual interest rate to the nearest tenth of a percent for 65,000 to grow to $65,783 with 91 cents. If interest is compounded monthly for 6 months. So we know the principal. We know the final amount. We know that the interest is compounded monthly, so n is 12. And for 6 months, that's going to be half a year. So that's going to be 6 out of 12 months. 6 months is half a year. And we need to find the interest rate. We're going to obtain the interest rate as a decimal. We need to write this as a percent. The final answer must be a percent. Okay, so 65,000 times 1 plus r over 12 to the 12 times 1/2 is 65,783 with 91 cents. Okay, so let's solve for r. Well, 12 times 1/2 is going to be 6. So let's see, we're going to divide this. So 1 plus r over 12. 12 times 1/2 is 6. And then this is $65,783 with 91 cents divided by 65,000. Next, we're going to take the 6th root. If 1 plus r over 12 raised to the 6th power is this quotient, then 1 plus r over 12 is going to be the 6th root. Well, technically, we should have plus or minus, but we know that the answer must be positive. So this is, I'm going to keep it as a fraction. 65,783 with 91 cents over $65,000. Subtract 1 from both sides. R over 12 is the 6th root of $65,783 with 91 cents over 65,000. And the interest rate is 12 times that. It's 12 times. the sixth root of 65,783 with 91 cents over 65,000. Remember that a number raised to the 1/6 is the sixth root of that number. So we're going to put all this in the calculator. This is 12 times. This is $65,783 with 91 cents divided by 65,000. And that is going to be raised to the 1/6. That's going to be the sixth root of that number. So I'm getting, okay, so that's quite high. Let's see. Yeah, I'm trying to see what happened. Yeah, because this is not correct, so that's order of operation. So let's try again. Okay, I see what's going. Yeah, I see what I'm doing wrong. It's because I'm not subtracting one. So let's, yeah, I need to subtract one. So I need to stop sharing. Yeah, so I need to subtract. Yeah, I wasn't subtracting one. Okay, we're going to try one more time. Okay, so let's do this again. So this was what? This was the sixth root. Okay, so this was the sixth root of $65,783 with 91 cents divided by 65,000. So that's raised to the 1/6 power. We need to subtract one. And then we're going to multiply by 12. So far, we have that this is approximately, yeah, this is not correct. This last one is not correct. So R is approximately, or R over 12 is approximately 1.002 minus 1. So R over 12 is approximately 0.002. So R is going to be approximately 12 times 0.002 or 0.024. Okay, so finally we have it. So the interest rate, let's see. The required interest rate is 2.4%. Okay, so the last part is going to be the number E and continuous growth. So let's suppose the following. So let's see what happens. The situation is that a $1 principal is deposited or is invested in an account paying 100% annual interest. We are going to find the amount after 1 year. If interest is compounded, Okay, we're going to do a few situations. If interest is compounded yearly, that is when the compounded frequency is 1. When it is compounded semi-annually. So semi, that means half and half. That's twice a year. When interest is compounded quarterly, in a year there are 4 quarters, so that's going to be 4 times. When interest is compounded monthly, and I'll do 3 more daily. So daily, banks, even when it's a leap year, banks consider daily interest, well, consider only 365 years. Let's say that is compounded hourly. So hourly, if there are 365 days, and each day has 24 hours, 365 times 24 is 8,760. And if for some reason it's compounded each minute. So there are 8,760 hours in a year, and each hour has 60 minutes. So multiply 8,760 by 60. That's going to be 525,600. And I could keep on going, like each second and so on, but I think that's enough to get the idea. So the principal is 1. The interest rate is 100% or also 1. The time is going to be, that's going to be after 1 year. So the amount is going to be the principal times 1 plus r over n raised to the n times 1, or n times t. So this is piece 1. This is 1 plus 1 over n. And if t is 1, that's going to be n times 1. So what I'm going to do is put this in Excel. What happens when this number increases? So I'm going to share this. Okay, so we have n. N is the frequency, and we have the amount A. So when the frequency is 1, the amount is going to be 1 plus 1 divided by n. That is the number in A2. And that's raised to the n power. So that's raised to the A2. So after 1 year, not surprisingly, after 1 year, the money duplicated. But we're going to increase the frequency when it happens semi-annually, quarterly, monthly, daily, each minute, or hourly, and every minute. Okay, I'll do one more thing. I'm going to shift this a little bit. And okay, we still have, so that's yearly, semi-annually, quarterly, monthly, daily, hourly, and each minute. So when interest is compounded semi-annually twice a year, that number is 2.25. Then if it's compounded quarterly, the number increases to approximately $2.44. Monthly, that's going to be $2.61 approximately. So that number keeps growing, but it tends toward a number that I'll tell you what the number is. So that's $2.71. If we increase it hourly, so it's not increasing by a lot. And each minute, and let's say by that we do it each second. Okay, so that's going to be what? That's going to be 5,000, 2,500, 525,600. And each second, there are 60 seconds in a minute. So each second, well, you see where this is going. So actually, it's not going to tend to infinity. It's going to approach a certain number, and that number is the number E. Okay, so we found the interest. So we have something called the number E. And that will involve continuous growth. So I'm trying to find the definition in the book. Okay, so okay, there. Okay, yeah, there it is. So that's the value of E. This on page 428. The value of E is approximately, well, that's what we found in Excel. Approximately what we find in Excel. So when the frequency keeps increasing, we did it every second. At the end, $1 invested at 100% will be approximately the number E. And that's the formula for continuous compounding. So we increase the frequency. We were doing every hour, every minute, every second. So if it increases continuously, the frequency will approach infinity. And the formula for continuous compounding is going to involve the number E. If P dollars are deposited at a rate of interest R, compounded continuously for 30 years, then the amount paid in dollars on deposit is given by the formula A equals P raised to the RT. So last example is going to be example 9. Okay, suppose that $5,000 is deposited into an account paying 3% interest, compounded continuously for 5 years. Find the total amount on deposit at the end of 5 years. The principal is 5,000. The interest rate is 3%. As a decimal is 0.03. And it's compounded continuously. So that's for 5 years. Okay, the amount is 5,000 times the number E raised to the 0.03 times 3. 0.03 times 3 is 0.09. And to the nearest cent. Okay, so let's put this in a calculator. This is 5,000 times the number E raised to the 0.09. And that's going to be 500. Let's see, so that's, okay, I made a mistake. Okay, I see what I'm doing wrong. So sorry, there was a mistake. This wasn't a 3, that was a 5. So this is 5. And this is 1 5. Okay, so let's try again. Yeah, so I was doing it for 3 years. We need to do it for 5 years. So this 5,000 times the number E raised to the 0.15. And that is $5,000, $5,809 with 17 cents approximately. So this $5,809 with 17 cents. Okay, so this is it. Thank you for listening.